All right, yesterday what you did is you looked at orbital diagrams. Now, the thing that you'll probably remember about orbital diagrams is you probably got sick and tired of drawing all of those circles and making X's through them. For example, neon. Neon you would have did 1S, put an X through it. 2S, put an X through it. 2P, you would have drawn the three circles, and then you would have gone again, following Hund's rule, in each of the orbitals, and then came back for my total of 10 electrons. Well, what I'm going to do is I'm going to show you a shorter way of doing orbital diagrams. And what this is going to do is it's actually going to look at total electrons instead of looking at each individual orbitals. So what we're going to have is we're going to have electron configurations. And electron configurations is just going to be a shorthand. It's a shorthand representation of an orbital diagram using total electrons, or the total number of electrons. Now, before we get done, or before we, I guess, go ahead and start doing this, is I want to go ahead and look at an S. And we said that an S only had one orbital. So in that one orbital, we have a total of 2 electrons that can be placed. In a P, we said that there were 3 orbitals, and that is the reason why you drew the 3 circles beneath a P sublevel. And again, 3 times 2, this is going to have a grand total of 6 electrons. A D had 5 orbitals, and again, 5 times 2, we're going to have a grand total of 10 electrons. And then the last one was an F, and we said that an F had 7 orbitals. And in those 7 orbitals, 7 times 2, we had a grand total of 14 electrons. So what I want to do is I want to look at bismuth. When I look at bismuth, and I look on the periodic table, bismuth has an atomic number of 83, so what we're saying is it has 83 electrons. Now again, what this is going to do is this is going to use that mnemonic that we came up with, 3s, 3p, 3d, 4s, 4p, 4d, 4f, and again, we're only going to have 4 sublevels after that. So 6s, 6p, 6d, 6f, and I think that might be able to get me far enough along. So what I'm going to do is I go ahead and draw my line, and I get 1s. And S, again, can only hold 2. So this is where the electron configuration comes in. What we're doing is we're placing total electrons up top instead of drawing these circles down below. We're not even going to need to do the circle, so you can just go ahead and forget about those in electron configurations. After 1s comes 2s. Again, an S is going to hold 2 electrons. Okay, draw my next line. I go 2p. A 2p has 6 electrons. Okay, coming back up here and looking our 3 orbitals, a p can hold a total of 6 electrons. After 2p comes 3s. And again, an S is going to hold 2. Okay, come back over here. 3p, then 4s. 3p, again, a p can hold 6. 4s is going to hold 2. Now, if I go ahead and stop right here, again, we need to place 83 electrons. So in order to know where to stop, let's just start adding these numbers. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2. Okay, right now we're sitting at 20 electrons. Okay, and we need to get up to 83. So after 4s, Okay, we're going to go a 3D. 3D 10. Again, we put the 10 down because a D is going to hold 10 electrons. We're going to go 4p. Again, a p will hold 6 of them. And then we'll go 5s, and an s is going to have 2. So again, we're going to go ahead and look my 20 plus my 10. Okay, 20 plus 10 is going to be 30. 36. 36 and 2 is going to be 38. So right now, I'm at 38 electrons. Okay, after 5s. After 5s is going to be my 4d. Again, d's are going to hold 10. After 4d comes 5p. Again, p's will hold 6 of them. After 6p comes 6s, and that'll hold 2. So again, let's go ahead and look. We've got 38 back here, plus these 10 gives me 48. 48 plus these 6 is 54, and then those 2. So right now we're at 56, and we need to go up to 83. So after 6s, and I better go ahead and fill this in case we need to get to it, 7s. But after my 6s comes 4f. Now again, let's find f. F is right here. Holds 14 electrons. So I'm going to go ahead and put my 14 up there, and before I go any further, maybe we should add this up. 56 and 14. Okay, we are at 70 electrons right now. Okay, after 4f comes 5d. D's can hold 10 of them. So again, let's add our 10, so we're at 80. And after 5D comes 6p. Now, when you look up here, a p can hold 6 electrons. But I'm at 80 right there. I need to go to 83 there. So all I have to do is put a 3 up there. Those numbers that are superscripted, those numbers have to add up to the total number of electrons. So when I add the 2, the 2, the 6, the 2, 6, 2, 10, 6, 2, 10, 6, 2, 14, 10, and 3, all of those numbers add up to 83. Now, let's go ahead and talk about using this in our 4 quantum numbers. If we go ahead and talk about this with our 4 quantum numbers, same thing applies, except you're going to have to do a little bit of work to figure these out. So let's go ahead and let's look at using the 4 quantum numbers. So 4 quantum numbers describe electrons 11, 29, and 72. So what I need to do is I need to find where electron number 11 is at. So we've got 2, 4, 6 is 10. Okay, so I know that number 10 is after the 2p6. So here is going to be number 11 for me. I know there is that other electron in there, but this is my number 11. It says go to now look at number 29. So, okay, here's 20, and 10 more would give me 30. So this D is going to look like this. So we've got 21, 22, 23, 24, 25, 26, 27, 28. There's number 29 for me. And then the last one's going to be number 72. Okay, right here 70 after the 4F14. So I'm going to go ahead and look here. Again, number 71 is right there. And then this one's going to be number 72. Now again, I know it looks like this because all 10 of them are placed. But my 72 is going to be right in there. So when we look at 11, 29, and 72. N, L, M, and S. Okay, remember what we said. N is this number right here. So for number 11, we're in the third energy level. For number 29, we are in the third energy level. And number 72, fifth energy level. Now, L was your sublevels. Okay? Again, when you remember sublevels, S, P, D, and F. S was a 0, P was a 1, D was a 2, F was a 3. So when I look up here, number 11 is in the S sublevel. The value of S is 0. When I go ahead and come over here to this one, we are in the D sublevel. The value of D is a 2. And when we look at the last one, number 72, again, it is in a D sublevel. So again, it is going to be a 2. Now, with M, we said M was the negative L to positive L. Now, below an S, okay, the value of S was 0. Well, there really is no negative or positive 0. We said the value was 2, so we're going negative 2 to positive 2, so negative 1, 0, positive 1. Same thing here. Negative 2, negative 1, 0, positive 1, and positive 2. So, with that 11th electron, again, it's in a 3s, so the value of that s is 0, okay, because again, there is only one orbital. When we look at number 29, when you look at this slash right here, it's in the positive 1 orbital. And when I look at this one here, again, it corresponds to that one there, and that one is going to be in the negative 1 orbital. And the last one was spin, and remember, spin was positive half, negative half. And it's however you draw your line. And again, if you remember, I said I always draw my first line is going to be my positive 1/2. So because my first pen stroke was that way, again, it's going to be positive 1/2. When I go over here to the 29th electron, that 29th electron is an opposite in orientation, so that's going to be a negative 1/2. And number 72, again, is going to match that first one, so it also is going to be a positive 1/2. When we go ahead and look at electron dot diagrams can be done the same way. What you do is you find your highest energy level. When I look there, I've got a 1, 2, 2, 3, 3, 4, 3, 4, 5, 4, 5. I've got a 6th energy level, a 4th energy level, a 5th energy level, and I have a 6th energy level. Now the element that we're doing is bismuth. The symbol for bismuth is Bi. So I go ahead and draw the symbol for bismuth. Now, with it, we're going to take and look at the 6th energy level, and we're going to look at both of the 6s. We're not going to care about the 4F, and we're not going to care about the 5D, because again, they are not our highest energy level. Remember what we said, S's go on the right side. When I look at this 6S, there are 2 electrons. So we're going to go ahead and put 2 dots over here on the right side. Now I've got a 6p3, so what I really need to do is I need to look within that 6p3. Because a p has 3 orbitals, if I follow Hund's rule, I'm going to go ahead and put it like this. And again, remember the numbers, negative 1, 0, positive 1. On top is my negative 1 orbital. My negative 1 orbital, there was only 1 electron. On the left side is going to be my 0 orbital. And in that 0 orbital, there was 1 electron also. And finally, on the bottom is going to be my positive 1 orbital. That positive 1 orbital also had 1 electron. So that's going to be my dot diagram for bismuth. Now one thing that I need to do, and again it's going to be with orbital diagrams and electron configurations, is everything is about stability. These atoms want to find a way to become stable or slightly more stable than what they already are. So there is a stability rule of thumb. And that stability rule of thumb just states that a filled or half-filled sublevel is slightly more stable than a sublevel that is not filled or half filled. And you might be asking yourself, well, what exactly does that mean? Well, what I'm going to do is I'm going to look at molybdenum. And when I look at molybdenum, molybdenum has 42 electrons. So what I'm going to do is I'm going to go ahead and begin filling in the electron configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, and finally 4d4. Now here's what I'm going to do. When I look at this 1s, those orbitals or that sublevel is filled. When I look at the 2s, it is filled. When I look at the 2p, it is filled. I come all the way over here to the 4p, it's filled. The 5s is filled. Now when I look at that 4d, it's not filled and it's not half filled. When I go ahead and look at it, it looks like this. 1, 2, 3, 4. What I need is I need one more electron to make it half filled. And what will happen by this stability rule of thumb is we will actually take one electron from here and move it over. Because this 5s actually looks like that. But when I take an electron away, when I take one electron from the s, that becomes half filled. I move that electron over here, and what happens is I have two half-filled sublevels. So this 5s2 became a 5s1. This 4d4 becomes a 4d5. What you will notice is, and I will tell you, we only borrow on two things. Anytime you have a d4, we will borrow to make it a d5. Anytime we have a d9, we will borrow to make it a filled d10. And the thing is, you always borrow from the closest s. Always borrow from the closest s. Now, if I were doing electron dot diagrams, you do the same thing. You find your highest energy level. When I look at molybdenum, my highest energy level is right there, 5. Because I've got 1, 2, 2, 3, 3, 4, 3, 4, 5, 4. And when I look there, again, I'm going to go ahead and fill in my symbol, MO, But when I look there, that S only has one valence electrons, so I'm only going to put one dot on the right side.